Look up at the night sky on a clear evening, and what do you see? A tapestry of stars, distant and serene, seemingly frozen in time, a familiar cosmic backdrop to our lives here on Earth. But what if I told you that this peaceful view is an illusion? That just beyond our solar system, within the very spiral arm of the galaxy we call home, secrets are waiting ancient, astonishing, and almost beyond imagination. Welcome to the Orion Arm, our corner of the Milky Way. You might know it as just one of the galaxy's great spiral arms, a structure full of stars and dust, but it's so much more than that. It's a realm of unanswered questions, hidden wonders, and cosmic puzzles that have fascinated astronomers and dreamers for generations. Think about it. We live inside this incredible structure, a place where stars are born and die, where nebulae glow with the light of newborn suns, and where mysteries linger in the dark spaces between them. The Orion Arm isn't some distant, abstract region of space. It's our neighborhood, our backyard, and like any neighborhood, it has its stories, some told, and others waiting just out of sight, whispering from the shadows of giant molecular clouds and drifting starlight. What treasures lie within these cosmic corridors? What have we overlooked and what remains undiscovered, so close we could almost reach out and touch it? In this video, we're setting out on a journey, not to some far-off galaxy, but right here into the heart of our own celestial home. We'll uncover the strange phenomena that defy explanation, the curious objects that challenge our understanding of physics, and the possibilities that stir our deepest sense of wonder. From rogue planets wandering alone in the dark to enigmatic signals that hint at something more, the Orion Arm holds stories that are wilder than science fiction. So come with me, let's pull back the curtain on the cosmos you thought you knew and explore what's really hiding in our galactic backyard. But to truly understand the secrets it might hold, we first need to understand our address within it. So let's define exactly what the Orion Arm is. Picture our Milky Way galaxy not as a simple swirl of light, but as a magnificent cosmic pinwheel with several grand, sweeping arms spiraling out from a brilliant central hub. Our solar system doesn't reside in one of the larger primary arms. Instead, we are nestled within a smaller spiral structure known as the Orion Cygnus Arm, or more commonly, just the Orion Spur. Think of it not as a main highway of stars, but as a significant bridge or an offshoot connecting two much larger galactic arms, the mighty Sagittarius Arm inward toward the galactic center, and the grand Perseus Arm further out. This local cosmic neighborhood is still unimaginably vast. The Orion Arm is roughly an incredible 3,500 light-years across and stretches for at least 10,000 light-years in length. Within that immense volume, it's home to an estimated 100,000 stars, along with spectacular star-forming regions like the iconic Orion Nebula, which gives the arm its name. Our own sun is located right on the inner edge of this arm, about 26,000 light-years from the supermassive black hole at the chaotic galactic center. This positioning is far more than just a random celestial coordinate. It's a key factor that has shaped the very possibility of our existence. Being here, in this quieter suburban limb of the galaxy, has granted us a relatively stable and peaceful environment. We are sufficiently far from the densely packed and radiation-filled galactic core, where stellar close encounters are frequent and violent supernovae are common. That distance has offered our planet a long-term stability crucial for the slow, gradual process of evolution to unfold. Yet, our location is not without its own unique perils. As we travel around the galaxy, our entire solar system slowly oscillates above and below the galactic plane, periodically passing through the denser, cloudier parts of the arm itself. These passages can potentially disturb the distant reservoir of icy bodies at the solar system's edge, sending comets showering inward in events that have, in the deep past, contributed to mass extinctions on Earth. So our cosmic address is a double-edged sword, a haven of stability that is still very much connected to the dynamic and sometimes dangerous flows of the greater galaxy. This perfect, precarious position might just be the very reason we are here to look up and wonder about it all. Now, if our position within the quiet Orion Arm provides a certain galactic stability, the immediate space surrounding our solar system offers another layer of profound and surprising quietude. We are not just drifting through a typical, dense interstellar medium. We are actually floating inside a vast, cavernous void known as the local bubble. This isn't a bubble made of some invisible film, but rather a 500 light-year wide sphere of exceptionally hot, incredibly thin gas, a supernova-forged cavity where our Sun and a handful of other local stars are just temporary residents. This enormous pocket of emptiness wasn't always here. Its origin story is written in violence and power, roughly 10 to 20 million years ago, which is a mere blink in cosmic time. A series of massive stars, dozens of them, were born in a cluster not far from our present location. These stellar titans lived fast and died young, ending their short lives in catastrophic supernova explosions. One after another, these blasts sent unimaginably powerful shockwaves screaming through the interstellar gas and dust around them. Like a cosmic snowplow, each successive wave pushed the surrounding material outward, piling it up into a dense, cool shell that now defines the outer boundary of this cavity. Meanwhile, the interior of the bubble was left filled with the superheated, ionized remains of those long-dead stars, a wispy plasma that is nearly 1,000,000 degrees Kelvin, yet so tenuous that it contains only about 1 atom for every 10 cubic centimeters of space. To put that almost impossible emptiness into perspective, the best vacuum chambers we can create on Earth are still far denser than the gas inside this local bubble. Residing within this structure has profound implications. That thin, hot gas might be sparse, but it emits a soft, diffuse X-ray glow that astronomers had to learn to see past to study the universe beyond. More importantly, this local emptiness acts as a kind of buffer. The dense shell of material that walls our bubble helps shield us from some of the higher energy cosmic rays that scream across the galaxy, particles that could otherwise constantly bombard our planet and its atmosphere. For the future of interstellar travel, this bubble presents both an opportunity and a challenge. A spacecraft venturing out from our solar system would, for the first few light years of its journey, be traveling through this relatively clear and unobstructed void, potentially encountering fewer hazards. But its ultimate destination would likely lie beyond the shell, in the far denser and more complex interstellar environment that defines most of the galaxy. So, our quiet corner of the Orion Arm is made even quieter by this local absence, a cosmic clearing carved by ancient stellar fire that provides our solar system with a uniquely peaceful and privileged vantage point on the universe. Yet, even within the relatively quiet expanse of our local bubble, the Orion Arm holds structures of such colossal scale and power that they dominate our night sky, silent monuments to the dynamic forces shaping our galactic backyard. One of the most breathtaking and enigmatic of these is a faint, ghostly arc of light that cradles the entire constellation of Orion. Known as Barnard's Loop, this immense nebula is a celestial wonder that has puzzled astronomers for over a century. To the naked eye, it's invisible, but through long exposure photographs, it reveals itself as a gigantic, faintly glowing crescent, stretching across an area of the sky equivalent to over 25 full moons laid side by side. This is no small, local cloud. It is a structure of almost incomprehensible scale, spanning nearly 300 light-years from end to end. We are not looking at a distant object far across the galaxy. We are looking at a titanic event happening right in our own stellar neighborhood, a cosmic signpost whose true nature we are only just beginning to understand. For decades, the origin of this vast loop has been a subject of intense debate. The central question is a profound one. Are we seeing the aftermath of a single catastrophic stellar death, or the collective breath of an entire family of newborn stars? One compelling theory posits that Barnard's loop is the remnant of a supernova, the expanding shell of debris blasted into space from a star that died a violent death millions of years ago. In this scenario, the shock wave from that ancient explosion would have slammed into the surrounding interstellar medium, compressing gas and dust and causing it to glow with the faint red light of hydrogen alpha emission that we see today. The perfectly arced shape would be the leading edge of that still expanding bubble of hot gas, a fossilized echo of a moment of incredible cosmic violence. However, a competing and perhaps more widely accepted theory suggests an even more powerful and ongoing source. This view connects the loop directly to the incredible stellar nursery it so perfectly encircles, the Orion Molecular Cloud Complex. At the heart of this complex lies the magnificent Orion Nebula, a tempestuous cauldron of star birth. Here, the trapezium cluster, a group of brilliant, massive, and fiercely energetic young stars, is constantly pouring unimaginable amounts of radiation and stellar winds into their surroundings. The combined effect of these stellar hurricanes from multiple stars could have acted like a cosmic blowtorch, carving out a vast cavity and pushing the surrounding material outward into the shell we observe as Barnard's loop. It becomes less a tombstone for a dead star and more a cradle, a protective boundary forged by the very act of creation itself. This intimate connection to the star-forming heart of Orion makes the loop far more than just a pretty picture. It is a crucial component in a vast, interconnected cosmic ecosystem. The immense pressure from the stellar winds and radiation that may have created the loop also serves to compress the gas and dust along its inner edge. This compression can trigger the gravitational collapse needed to form a new generation of stars, meaning the loop could be actively participating in the very process of stellar birth it helped to initiate. It's a beautiful feedback loop of creation and destruction, where the energy from young stars shapes their environment, which in turn gives rise to even more stars. Barnard's loop stands as a silent, glowing testament to the fact that our galactic backyard is not a static museum exhibit, but a dynamic, evolving, and intensely active region where the great cycles of stellar life and death are continuously playing out on a scale that dwarfs our entire solar system. And right at the very heart of Barnard's loop, at the center of this grand celestial stage, lies its most famous and brilliant occupant, the Great Orion Nebula. Known to astronomers as Messier 42, it's that faint, fuzzy patch you can just barely make out with the naked eye in the sword of the Orion constellation. But this is no faint smudge. It is a raging cosmic cauldron, a stellar nursery so close and so active that it serves as our primary window into the violent and beautiful process of star birth. Located a mere 1,300 light-years away, it is the closest massive star-forming region to Earth, offering us an unprecedented front-row seat to watch the universe build new solar systems in real time. What appears to our eyes as a single, glowing cloud is actually the brightest part of a much vaster structure known as the Orion Molecular Cloud. This entire complex is a chaotic and dynamic environment, but the nebula we see is a specific region where the action is most intense. It is an emission nebula, meaning it doesn't just reflect light from nearby stars, it actually generates its own light. The engine behind this brilliant glow is a tight cluster of incredibly hot young stars called the trapezium cluster. The fierce ultraviolet radiation blasting from these massive newborns is so powerful that it strips electrons away from the atoms of the surrounding hydrogen gas, a process called ionization. When those electrons eventually recombine with protons, they release that energy as the characteristic red and pinkish glow that makes the nebula so visually stunning. We are essentially watching a cosmic light show powered by the raw energy of infant suns. But the real magic of the Orion Nebula isn't just in the light it emits, it's in the shadowy structures hidden within it. The Hubble Space Telescope, peering deep into its heart, has revealed one of the most significant discoveries in modern astronomy: proplyds, or protoplanetary disks. These are flattened, spinning disks of gas and dust that swirl around brand new stars. They are the raw material from which planets are built. Hubble's images show them as tiny, dark silhouettes against the nebula's bright background, like flying saucers caught in a cosmic spotlight. Some are seen face-on, revealing their vast, dusty plains, while others are seen edge-on, appearing as dark slashes cutting across the glow. Within these disks, microscopic dust grains are colliding, sticking together, and slowly, painstakingly assembling themselves into larger rocks, then planetesimals, and eventually full-fledged planets. We are not just looking at star birth, we are witnessing the very origins of entire solar systems, seeing the first steps in a process that, in our own neighborhood, eventually led to the formation of Earth and the other planets. The environment within which these nascent solar systems are trying to form is anything but peaceful. It is a cosmic demolition derby filled with both creative and destructive forces. The very same ultraviolet radiation that makes the nebula glow is also a destructive torrent, actively eroding the outer layers of the proplyds closest to the trapezium stars. For a young planetary system, its ultimate fate depends largely on its location. Those that form far enough away from the massive stars might survive long enough for planets to coalesce. Those that form too close have their gaseous envelopes violently stripped away, potentially truncating planet formation and leaving behind a system of barren, rocky worlds. It's a stellar paradox where the energy that illuminates the nursery also threatens its youngest occupants. This leads to a profound and tantalizing question: could any of these fledgling worlds forged in such chaos ever become habitable? The ingredients are certainly all there. Spectroscopy has revealed that the nebula's clouds are rich in complex organic molecules, the basic building blocks of life as we know it. These molecular precursors are being manufactured in the nebula itself and are being incorporated into those spinning protoplanetary disks. While the intense radiation near the core would likely sterilize any forming planet, there are countless stars being born in the quieter, darker outskirts of the molecular cloud. Around these more solitary, sun-like stars, planetary systems could be forming in a far more stable environment, their newborn worlds already seeded with the organic compounds necessary for life. The Orion Nebula, therefore, is more than a spectacle, it is a factory. It forges new stars, assembles new planets, and may be one of the universe's great distributors of the primordial soup from which life itself can eventually emerge. But for all the brilliant light and vibrant creation happening within nebulae like Orion, the Orion Arm also harbors its share of ultimate darkness regions where gravity has won a total and terrifying victory. We're talking about black holes, and while the supermassive black hole at our galaxy's core gets all the attention, a more stealthy and perhaps more immediate kind could be drifting through our neighborhood right now: stellar mass black holes. These are the ghosts of dead stars, and they are likely far more common and far closer than we ever realized. These gravitational monsters begin their lives as the most massive stars in the cosmos. Imagine a star born with 20, 30, or even 50 times the mass of our own Sun. These titans live fast and furiously, burning through their nuclear fuel in just a few million years. When that fuel finally runs out, the outward pressure from fusion can no longer hold back the star's own immense gravity. What happens next is one of the most violent events in the universe: a core collapse supernova. The star's outer layers are blasted into space in a cataclysmic explosion, visible across the galaxy. But the core, the star's heart, undergoes an even more radical transformation. It collapses inward, not stopping at the density of a neutron star, but continuing to compress until its gravity becomes so powerful that not even light can escape its pull. A stellar mass black hole is born, typically packing several times the mass of our Sun into a region of space smaller than a city. The challenge, and the reason they remain so hidden, is right there in the name black. They don't emit any light of their own, so how do you find something that is, by its very nature, invisible? Astronomers have to become cosmic detectives, looking for the telltale clues these objects leave on their environment. The most successful method has been to find them in binary systems, where the black hole orbits a companion star. As the two objects dance around each other, the black hole's immense gravity can pull stellar material from its partner. This stolen gas doesn't fall directly in. It first spirals into an incredibly hot, rotating disk around the black hole called an accretion disk. Friction within this disk heats it to millions of degrees, causing it to glow intensely with X-rays, a brilliant beacon that betrays the presence of the dark monster at its center. By carefully measuring the wobble of the visible star, we can also calculate the mass of its unseen companion. If that mass is too great to be a neutron star and we see those telltale X-rays, we've found one. But what about the black holes that are completely alone, drifting silently through the void without a star to snack on? These lone wolves are infinitely harder to find, but we have one more tool: gravitational microlensing. This occurs when such a black hole passes almost directly between Earth and a distant background star. Its gravity acts like a lens, bending and magnifying the background star's light for a brief period, a few days or weeks. From the distinctive brightening and fading of that star's light, we can infer the mass and presence of the invisible object causing the distortion. It's a fleeting glimpse, a shadow passing in the night, but it tells us these solitary black holes are out there. And this leads to a rather sobering thought. Based on our understanding of how many massive stars have lived and died in the Milky Way, astronomers estimate there could be as many as 100 million stellar mass black holes roaming our galaxy. Statistically, many of them must be here in our own Orion Arm. The closest known black hole, Gaia BH1, is located about 1,500 light-years away, well within our galactic neighborhood. But for every one we find, there are likely countless others we have yet to detect. Given the dynamic nature of our spiral arm, with its history of supernova and stellar movement, it is not just possible but probable that one of these dark remnants is passing through our corner of the galaxy right now, perhaps even within just a few dozen light-years of our solar system. The idea is less science fiction and more a statistical certainty. They are the ultimate hidden monsters of our galactic backyard, silent, dark, and forever drifting through the spaces between the stars. Yet for all their dark and silent menace, the Orion Arm is also home to celestial objects of breathtaking speed and brilliant light, cosmic projectiles that tear through the void and leave a visible scar on the fabric of space itself. These are the runaway stars, stellar renegades ejected from their birthplaces and sent careening across the galaxy at velocities that defy comprehension. Imagine a star not as a fixed point of light, but as a solitary traveler on an endless high-speed journey, blazing a trail through the cold interstellar medium and creating some of the most dramatic and beautiful structures we can observe. The story of how a star becomes a runaway is a tale of cosmic violence and gravitational chaos. These stars don't just decide to leave home, they are violently evicted by one of two powerful mechanisms. The first is a gravitational slingshot, often within a dense young star cluster. In these crowded stellar nurseries, complex gravitational dances between multiple stars can easily occur. Sometimes, a close encounter between a binary star system and a more massive single star can result in a gravitational transfer of energy. The more massive star can steal momentum, flinging the smaller binary system away at high speed while it itself gets a kick in the opposite direction. It's a celestial game of billiards on an unimaginable scale, with stars as the balls. The second, and even more explosive ejection method is a supernova kick. In a binary system where two stars are locked in a mutual orbit, one of them reaches the end of its life and detonates. The sudden, asymmetric loss of mass in the supernova explosion is like removing one leg from a stool. The entire system becomes instantly unbalanced. The remaining star, now freed from the gravitational bond of its obliterated partner, is flung away at the velocity it was originally orbiting, a survivor rocketing away from the scene of a catastrophic death. Regardless of the method, the result is the same: a star set adrift, destined to spend its life alone, crossing vast stretches of interstellar space at speeds that can exceed 100,000 miles per hour. Perhaps the most magnificent example of such a cosmic speedster is Zeta Ophiuchi, a stellar behemoth that commands attention. Located about 460 light-years away, it is a hot, blue, massive star that weighs in at nearly 20 times the mass of our Sun and shines with a luminosity 68,000 times greater. But its true claim to fame is its motion. Zeta Ophiuchi is hurtling through space at a staggering 24 miles per second, or nearly 90,000 miles per hour relative to its surroundings. We know it's a runaway because we can trace its path directly backward to a group of stars in the Scorpius-Centaurus association, the very stellar nursery that kicked it out millions of years ago. The true spectacle, however, lies not in the star itself, but in the magnificent wake it creates. As this stellar cannonball plows through the interstellar medium, it behaves like a speedboat rushing across a calm lake. The star emits a powerful stellar wind, a constant stream of charged particles flowing from its surface. This wind rams into the stationary clouds of gas and dust that fill the space between stars, and the collision is violent and luminous. The material piles up directly in front of the star, becoming compressed and heated to extreme temperatures, glowing in intense infrared light. This forms a characteristic bow shock, a parabolic wave that wraps around the star like a cosmic cocoon. In the case of Zeta Ophiuchi, this bow shock is immense, spanning several light-years across. To our telescopes, it appears as a brilliant, rippling arc of glowing material, a perfect testament to the star's incredible journey. These runaways are far more than just beautiful accidents. They are powerful agents of change within the Orion Arm. As they race through different galactic environments, they inject enormous amounts of energy and momentum into otherwise quiet regions of space. The powerful shock fronts they generate can sweep up material, compressing interstellar gas and potentially triggering the collapse of clouds to form new stars, even as they themselves continue their lonely exile. They serve as natural probes, allowing astronomers to study the density and structure of the invisible interstellar medium by observing how it shapes the bow shocks. And for our solar system, their passage, while statistically rare, is a reminder of the dynamic and sometimes hazardous nature of our galactic neighborhood. A close encounter with such a massive, fast-moving star could gravitationally disrupt the Oort cloud at the solar system's edge, sending a shower of comets inward. The runaway stars are the restless nomads of our spiral arm, eternal reminders that even in the vastness of space, no journey is ever truly peaceful. Now, if runaway stars are the solitary speedsters of our arm, then the good belt is the grand architectural structure they sometimes call home, a colossal, tilted ring of young stars, brilliant clusters, and star-forming clouds that defines the entire scale of our local cosmos. This isn't a small feature, it's a vast, disk-like structure nearly 3,000 light-years across, and we are living right inside it. Its most famous residents include some of the most recognizable patterns in our sky: the stars of Orion's belt, the bright glow of Sirius, the scintillating jewels of the Scorpius-Centaurus association, and the spectacular Pleiades and Hyades clusters. These aren't randomly placed, they are all part of this single, gigantic, and oddly tilted ring that encircles us. What makes the good belt so immediately fascinating is its orientation. While most of the galaxy's stars and gas rotate in a relatively flat plane, like cars on a racetrack, the good belt is tilted at a pronounced angle of about 20 degrees to that galactic plane. Imagine a huge dinner plate that's been knocked slightly askew on a massive table. That's essentially the relationship between this local ring of stars and the rest of the Milky Way disk. This tilt is the first major clue that this structure has a unique and violent origin story, one that astronomers are still working to fully decipher. So how did this gigantic, tilted ring come to be? The prevailing theory points to a single, catastrophic event that sent a powerful shockwave rippling through our galactic neighborhood. The most likely culprit is an ancient supernova explosion, but not just one. The leading idea suggests that multiple massive stars born together in a long-vanished cluster lived out their short lives and then died in rapid succession. Their supernova would have occurred in a chain reaction, each blast reinforcing the last, creating a collective shockwave of immense power. This wave then expanded outward like a fiery bubble, sweeping up the surrounding interstellar gas and dust into a dense, massive shell. Gravity then took over, causing this compressed shell to fragment and collapse, seeding the birth of the brilliant new stars and star clusters that now outline the belt. In this scenario, the tilt could have been inherited from the original motion or location of that first triggering cluster. An alternative and equally dramatic hypothesis proposes a collision from outside. Billions of years ago, a small dwarf galaxy or a massive dark matter-dominated superhalo could have plunged directly through the plane of our Milky Way. The gravitational disturbance from such a high-speed impact would have sent powerful ripples through the galactic disk, violently perturbing the gas and stirring it into a new, off-kilter configuration that later condensed to form the stars of the Good Belt. This theory elegantly explains the large-scale tilt and the coherent motion of the stars within the belt, as they would all share the momentum imparted by that ancient galactic-scale collision. Regardless of its precise origin, the Good Belt's impact on our cosmic vicinity is undeniable and ongoing. It is the epicenter of the most recent period of star formation in our galactic neighborhood. The vast molecular clouds that are part of this structure, like the Orion molecular cloud we explored earlier, are the active factories where this process continues today. The belt is not a static relic, it is a dynamic and evolving engine of creation. The massive stars within it live fast and die young, and their eventual supernova deaths will themselves trigger the next wave of star formation, continuing a cycle that has been playing out for millions of years. This means our solar system's journey through the galaxy is also a journey through this evolving structure. As we orbit the galactic center, we are currently passing through the Good Belt, and we have been for millions of years. This passage has directly influenced Earth's own environment. The rate of supernova within the belt is higher than in the quieter galactic regions outside it. Some scientists have proposed that nearby supernova, occurring within the Good Belt over the past 10 to 15 million years, could have periodically affected Earth's climate by bombarding the upper atmosphere with increased cosmic rays, potentially influencing cloud cover and even contributing to past extinction events. Our local cosmic architecture, therefore, is not a distant backdrop. It is an active participant in the history of our planet, a testament to the profound interconnectedness of the universe on the grandest and the most personal of scales. But between the blazing speed of runaway stars and the grand architecture of the Good Belt lies the very raw material that makes it all possible: the dark, cold, and impossibly vast molecular clouds. These are not the bright, glowing nebulae we see in photographs. They are their dark and dusty precursors, the true nurseries and hidden vaults of the galaxy. To understand how stars are born, we must venture into these cosmic wombs, and two of the most significant in our local arm are the Taurus molecular cloud and the Rho-Ophiuchi cloud complex. The term molecular cloud itself reveals their secret. In most of space, atoms like hydrogen float around individually, but within these colossal structures, conditions are just right. Cold enough and dense enough for atoms to link up and form molecules, primarily molecular hydrogen. This is the fundamental fuel for star formation, but these clouds are far more than just simple hydrogen gas. They are a rich, complex soup, They contain helium and, crucially, they are filled with tiny silicate and carbon-based dust grains no larger than particles of smoke. These microscopic bits of dust are utterly essential as they provide surfaces for chemical reactions, and most importantly, they act as a coolant. By radiating away heat, they allow dense clumps within the cloud to collapse under their own gravity, overcoming the internal pressure that would otherwise keep them puffed up. Each major cloud in our arm has its own unique character and role in the cosmic ecosystem. The Taurus molecular cloud, for instance, is a relative stone's throw away at about 450 light-years. It is a quieter, more serene nursery compared to the grand Orion complex. Here, star formation is a slower, more isolated process, giving birth predominantly to gentle, solitary red dwarf stars and a rich harvest of young stellar objects still swaddled in their gaseous envelopes. It's a cosmic laboratory for studying the earliest, most delicate stages of how a star like our Sun begins its life, away from the disruptive violence of massive stellar siblings. In stark contrast, the Rho Ophiuchi cloud complex, situated near the bright star Antares, is a vibrant and chaotic tapestry of creation. It's actually one of the closest star-forming regions to us at just over 400 light-years away. What makes Rho Ophiuchi so visually spectacular is the interplay between its dark dust clouds and the brilliant light of nearby young stars. The cloud's dust doesn't just block light, it also scatters and reflects it, creating stunning blue reflection nebulae that look like ethereal veils. Meanwhile, in its darker, denser cores, massive new stars are igniting, their intense ultraviolet radiation energizing the surrounding hydrogen gas and causing it to glow with the deep red signature of an emission nebula. Rho Ophiuchi is a multi-phase factory, showcasing every step of the stellar birth process in one dazzling, chaotic region. This immense density, which allows for the birth of stars, also creates their greatest hiding place. The darkest patches within these clouds, known as dense cores, are so thick with dust that they become completely opaque to visible light. They act as a cosmic cloak, shielding the violent and beautiful processes happening within from our prying eyes. An entire solar system could be assembling itself deep inside one of these cores, and from our vantage point, it would be utterly invisible, a secret guarded by a wall of dust. We can only peer into these nurseries by using telescopes that see in other parts of the spectrum, like infrared light, which can penetrate the dust and reveal the warm, young stars taking shape inside. This dual nature is what makes molecular clouds so fascinating. They are both cradles and veils. They are the essential factories of the galaxy, without which there would be no new stars, no new planets, and ultimately, no new ingredients for life. Yet, they also represent the final frontier of obscurity within our own galactic backyard. They remind us that for all we have learned by looking up at the stars, some of the universe's most profound secrets are still hidden in the dark, waiting for the right technology and the right moment to reveal themselves. But beyond the visible tapestry of stars and gas, beyond the glowing nebulae and the dark molecular clouds, lies the deepest and most pervasive mystery in all of modern cosmology, a secret that underpins the very structure of our galactic arm and yet remains completely invisible to us: dark matter. We've mapped the stars, we've measured the gas, but when we add up all that visible mass and calculate how it should gravitationally influence the motion of objects within the Orion Arm, the numbers fall catastrophically short. The stars at the edges of our galactic neighborhood are moving far too quickly, orbiting the galactic center with speeds that should, according to the laws of physics, send them flying off into the intergalactic void. Something else, something unseen, must be providing the extra gravitational glue to hold everything together. That something is dark matter, and its presence here in our own backyard is both a fundamental puzzle and the key to understanding the true architecture of our home. So how do you detect something that doesn't emit, absorb, or reflect any light whatsoever? astronomers have to become masters of inference, studying the effects of this invisible material on the things we can see. The primary method is to carefully chart the rotation curve of the Milky Way. This involves precisely measuring the orbital velocities of stars and clouds of hydrogen gas at different distances from the galactic center. In a simple solar system model, planets farther from the Sun move more slowly, like Pluto compared to Mercury. But in a galaxy, the velocity of stars remains constant or even increases with distance from the center. This flat rotation curve is the most direct and compelling evidence for a massive, invisible halo of dark matter that envelops the entire galaxy, its gravitational influence dominating even in the far outskirts. We can't see the halo, but we can see the stars whizzing around faster than they should be, and that tells us the halo is there, its pull keeping them in check. But the question for us right here in the Orion Arm is more localized. How is this dark matter distributed within our own spiral arm? Is it smooth, like an invisible fog, evenly permeating the space between stars? Or is it clumpy, concentrated into dense streams and subhalos that orbit within the larger galactic halo? This is an area of intense and ongoing research. By studying the subtle motions and interactions of local stars and gas clouds with exquisite precision, using data from telescopes like Gaia, scientists are trying to detect the slight gravitational tugs that would betray the presence of a nearby clump of dark matter. It's like trying to sense the presence of a silent, invisible ship by watching the ripples it makes on the surface of a dark sea of stars. Some theories even suggest that a dense, dark matter hurricane might be passing through our solar system right now, a stream of particles left over from a dwarf galaxy consumed by the Milky Way billions of years ago, yet we would feel no physical sensation from it at all. Understanding the local density and behavior of this enigmatic substance isn't just an academic exercise. It's absolutely crucial for building a true map of our galactic backyard. If we want to know the total mass of the Orion Arm, and therefore its true gravitational influence, we must account for this invisible component. It affects everything from the long-term stability of our solar system's orbit to the rate at which the arm itself rotates around the galactic center. Furthermore, countless experiments here on Earth are hunting for direct evidence of dark matter particles. These detectors, tucked away in deep underground labs, are waiting for the incredibly rare moment when a dark matter particle bumps into a regular atom. Their chances of success depend entirely on accurate models of how much dark matter is in our local neighborhood and how it's moving. If our estimates of its local density are wrong, we might be looking for a signal that is far weaker or stronger than we predicted. The invisible architecture of dark matter doesn't just hold the stars in place. It holds the answers to some of the most profound questions about the nature of matter, gravity, and the ultimate fate of our entire galaxy. And just as we're coming to terms with the invisible architecture of dark matter, a stunning discovery has completely rewritten the map of our immediate cosmic neighborhood, revealing a structure of such elegant and unexpected beauty that it challenges our most fundamental ideas about the shape of our galactic arm. For decades, astronomers pictured the gas clouds between nearby stars as a relatively formless collection of spheres and blobs, but that all changed in 2020 with the analysis of data from the European Space Agency's Gaia mission. By meticulously plotting the three-dimensional positions and motions of young stellar clusters and the nurseries they're born from, a team of researchers uncovered something extraordinary: a vast, undulating river of star-forming gas, a continuous wave that arcs through space right on our celestial doorstep. They named it the Radcliffe Wave after the Radcliffe Institute for Advanced Study where the discovery was made. This is not a small feature. The Radcliffe Wave is truly colossal, a sinusoidal structure that stretches for an astonishing 9,000 light-years and is more than 4,000 light-years wide at its broadest point. To grasp its scale, imagine a ripple in a pond, but one so vast that our entire solar system would be but a speck on its surface. This wave doesn't just exist near us, we are part of it. Our Sun, along with its protective local bubble, is currently passing through this immense structure, having entered it about 13 million years ago and expected to remain within it for another 10 million years to come. The most famous stellar nurseries we know and love, the Orion, Taurus, Perseus, and Cepheus molecular clouds, are not randomly scattered dots. They are the brightest crests of this single, continuous wave, like the whitecaps on a rolling ocean swell. They are all connected, integral parts of a unified and breathtakingly massive celestial formation. The very existence of such a perfect wave pattern, this beautiful, coherent sinusoid, is a direct challenge to older, simpler models of our galaxy's structure. It forces us to ask a profound question: what could possibly create and sustain such a perfectly undulating shape across thousands of light years? The leading hypothesis points to the gravitational influence of a spiral density wave. This is a theory that explains the very existence of the majestic spiral arms we see in galaxies like our own. The arms aren't permanent structures made of the same stars. Instead, they are like traffic jams moving through a city. As stars and gas clouds orbit the galaxy, they enter a region of compressed gravity, the spiral density wave, which slows them down, piles them up, and triggers star formation. The Radcliffe Wave could be a local manifestation of this grand process, a ripple within a ripple, its precise motion governed by the larger gravitational dance of the entire Milky Way. However, another compelling theory suggests a far more violent and dramatic origin story, a past collision. Billions of years ago, a small dwarf galaxy or a massive dark matter subhalo. The invisible scaffolding of the cosmos could have sideswiped or plunged directly through the disk of our Milky Way. The gravitational shockwave from such a cataclysmic event would have sent a powerful ripple through the galactic plane, much like a pebble dropped in a pond, setting the gas in our local region oscillating in this precise, wave-like pattern that we observe today. This would make the Radcliffe Wave a fossilized echo of an ancient galactic-scale accident, a permanent scar left on the face of our galaxy that we are only now able to see. What's truly remarkable is that this wave is not static, it is dynamic and moving. The entire structure is oscillating through space, much like a wave travels across the ocean. The gas and the young star clusters within it are flowing along this celestial current, riding the wave. This ongoing motion provides astronomers with a unique natural laboratory. By studying its kinematics, how different parts of the wave are moving, scientists can essentially perform a galactic-scale experiment in physics. They can weigh the gravitational forces at play, measure the pressure of the interstellar medium, and better understand the feedback processes where newborn stars, through their winds and radiation, in turn shape the gas that birthed them. The Radcliffe Wave is more than a static map. It is a living, breathing entity that allows us to observe the dynamic processes of galaxy evolution happening in real time, right in our own backyard. This incredible discovery fundamentally changes our perspective. It shows us that our local cosmos is not a quiet, random collection of objects, but is instead organized on a scale we are only beginning to appreciate, shaped by forces both immense and subtle. The Radcliffe Wave is a testament to the fact that even after centuries of looking up, our galactic home still has the power to surprise us with its hidden structures and elegant patterns, reminding us that the greatest secrets are often hiding in plain sight, waiting for the right moment to reveal their true form. But as we chart these grand waves of gas and newborn stars, we must also turn our attention to the shadowy, elusive residents that may far outnumber them all, the true ghosts of the Orion Arm, known as brown dwarfs. Often called failed stars, these mysterious objects occupy a strange and fascinating limbo in cosmic classification. They form like stars from the collapse of a gas cloud, but they simply never accumulate enough mass to ignite the sustained nuclear fusion of hydrogen that defines a true star. They are too massive to be considered planets, yet not massive enough to truly shine, destined to cool and fade into near invisibility over billions of years. Detecting these cosmic phantoms is one of the greatest technical challenges in modern astronomy. Their primary signature is not visible light, but a faint glow of heat infrared radiation. In their youth, they are relatively warm, perhaps a few thousand degrees, and can glow a dim magenta or red. But as they age, they cool rapidly, their emissions sliding down the infrared spectrum into wavelengths that are incredibly difficult to observe from within our own atmosphere. To find them, astronomers must rely on specialized infrared telescopes and a meticulous process of elimination. A common method involves scanning the sky for objects that appear very red and very faint. Follow-up observations then check for the presence of lithium in their atmospheres, a key chemical clue. In a true star, lithium is quickly destroyed by nuclear reactions, but in a brown dwarf it can persist, a telltale sign of an object that never quite made the stellar grade. The search within our own galactic neighborhood has revealed that these failed stars are not rare anomalies. They might be one of the most common populations in the entire Orion Arm. Initial results from extensive infrared sky surveys suggest a startling possibility. For every ordinary star like our Sun, there could be as many as 2 or even 3 brown dwarfs drifting unseen through the darkness. This implies there may be hundreds of billions of these objects filling our galaxy, with a significant fraction residing right here in our spiral arm. They are the universe's silent majority, a vast hidden populace of almost stars. This leads to a captivating and slightly unsettling thought. Given their sheer numbers and our difficulty in spotting the coolest, oldest ones, it is statistically almost certain that several of these dark, Jupiter-like orbs are lurking in the extreme outskirts of our own solar system, far beyond Pluto in the frozen realm of the Oort cloud. While they would be too distant and too faint to exert any noticeable gravitational pull on the known planets, their presence would mean our solar system is not entirely isolated. We could be sharing our space with ancient, cold, and failed stars that have been drifting alongside us for billions of years, completely undetected. They represent the ultimate hidden inhabitants of our galactic backyard, a testament to the fact that the most common objects in the universe may also be the ones most adept at hiding from our view. And yet, while we scan the darkness between the stars for these ghostly brown dwarfs, one of the most captivating astronomical mysteries of our time might be pointing to a hidden object much closer to home, an enigma that could tie our solar system directly to the dark secrets of the Orion Arm itself. I'm talking about the hunt for Planet 9. This isn't about Pluto, that debate is settled. This is a compelling, evidence-driven hypothesis that a true 9th planet, a world larger than Earth and colder than ice, could be orbiting in the profound blackness far beyond Neptune. The clues for its existence aren't a direct sighting, but rather the strange and clustered orbits of a group of small, icy bodies in the distant Kuiper belt. These objects, known as trans-Neptunian objects, don't have orbits that are randomly scattered. Instead, their closest approaches to the Sun are all grouped together in space, and their orbits are tilted in a similar direction, as if they are all being shepherded by the immense gravity of a single, unseen shepherd. The math is persuasive. For their orbits to be grouped so specifically, the probability of it happening by pure chance is astronomically low, less than 0.0002%. A massive planet with an estimated 5 to 10 times the mass of Earth on a wildly elongated 15,000 to 20,000 year orbit would perfectly explain this gravitational grouping. Its distant tug would act like a hidden hand, organizing these smaller icy worlds into the peculiar configuration we observe. Yet, for all the compelling orbital evidence, the search has so far come up empty. Our most powerful telescopes have scanned the vast regions of sky where it could be hiding and found nothing. This begs a profound question. Are we failing to find it simply because it's incredibly faint and distant? Or could there be a more exotic explanation rooted in the dynamics of our local galactic environment? This is where the mysteries of our solar system and the Orion Arm collide. What if the gravitational perturber isn't a planet that formed with our solar system at all? What if it's an intruder? The Orion Arm is likely teeming with rogue planets, worlds untethered to any star, cast adrift by gravitational interactions in their birth systems. These nomadic worlds are predicted to outnumber stars in our galaxy, and many of them are undoubtedly drifting through our spiral arm. It is entirely plausible that one of these rogue planets, perhaps an ice giant like Neptune that was ejected from its own star system long ago, could have been captured by the Sun's gravity during a close encounter. It would now be a permanent, yet incredibly distant, member of our solar family, its orbit forever marked by its chaotic origins rather than a calm, primordial formation. But the possibilities get even stranger. The gravitational shepherding we see in the outer solar system might not be from a single object. Could it be the collective influence of a previously unknown population of massive objects lurking in the extreme dark? A swarm of large, dark bodies, perhaps a cluster of these very same rogue planets, or an abundance of super-Earths that our models didn't predict for our own solar system, could together create a similar gravitational effect. Alternatively, the perturbing influence might not even originate within our solar system. A faint, distant stellar companion to our Sun, a small brown dwarf or a red dwarf orbiting far out in the Oort cloud, a hypothetical object sometimes called Nemesis, could periodically disturb the inner Oort cloud, sending comets inward and potentially shepherding the orbits of these distant Kuiper belt objects in a way that mimics a single large planet. The ongoing search for Planet 9, therefore, is about much more than just finding a new world. It is a direct test of our understanding of how solar systems form and how they interact with their galactic neighborhood. If Planet 9 is found and confirmed to be a captured rogue planet, it would be a stunning revelation. It would prove that our solar system is not a closed, isolated system, but an open one that can acquire new planets over its lifetime, stealing them from the vast population of nomads that we now know travel the spaces between the stars. It would be the ultimate prize, a direct piece of the Orion Arm right here in our own celestial backyard, a permanent reminder of the dynamic and interconnected nature of our spiral arm. The hunt continues, and with every scan of the heavens, we're not just looking for a planet, we're probing the hidden gravitational fabric of our local cosmos, searching for a clue that connects the story of our Sun directly to the dark, wandering secrets of the Orion Arm. And if the possibility of a captured rogue planet at the edge of our own solar system sparks the imagination, consider the sheer, staggering scale of this phenomenon across the Orion Arm itself. We are not talking about a handful of lonely worlds. We are confronting a hidden population of cosmic nomads that may outnumber the stars we see in the night sky. These are rogue planets, worlds completely untethered from the gravitational embrace of any parent star, condemned to an eternal journey through the freezing, lightless void of interstellar space. Their existence transforms our mental image of a galaxy from a collection of well-ordered solar systems into something far more dynamic and wild, a place where countless orphaned worlds drift like ghosts in the darkness between the stars. The origins of these solitary travelers are as violent as they are fascinating. The primary birth canal for a rogue planet is a gravitational ejection from its native star system. In the chaotic early days of a young solar system, when dozens of protoplanets are jostling for position in a crowded orbital dance, close encounters are inevitable. A budding gas giant like a young Jupiter can exert a tremendous gravitational pull on a smaller neighboring world. In a cosmic game of pinball, the larger planet can steal momentum from the smaller one, flinging it out of the system entirely at tremendous speed, sending it careening into the galactic deep. Another catastrophic event is the death of a binary star system. If two stars are locked in a mutual orbit and one of them goes supernova, the sudden, asymmetrical explosion can disrupt their gravitational balance, potentially kicking the surviving star's entire family of planets out into the void. In a single, violent moment, a world that once knew the warmth of a sun is cast adrift, its atmosphere freezing solid and its oceans turning to global glaciers in a geological instant. But there's an even more intriguing possibility. Some of these worlds may never have known a sun at all. Within the vast, dark molecular clouds that weave through our spiral arm, small knots of gas and dust can collapse under their own gravity. If a clump isn't quite massive enough to ignite into a star but is still larger than a planet, it can form directly from the interstellar medium, a planet born of darkness, destined to never feel the warmth of a nuclear furnace. These solitary formations would be true independent entities from their very first moment, drifting away from their cold nursery to begin an infinite, sunless journey. Finding these dark, frozen wanderers is one of the most difficult challenges in modern astronomy, since they emit almost no light of their own, especially after they've cooled over millions of years. Traditional optical telescopes are nearly useless. Astronomers must instead become detectives of subtle gravitational effects, primarily using a technique called microlensing. This occurs when such a rogue planet passes almost perfectly between Earth and a distant background star. The planet's gravity, warping the fabric of spacetime itself, acts like a lens, bending and focusing the light from that faraway star. For a period of time ranging from a few hours to a couple of days, the background star will temporarily appear to brighten as the rogue planet's gravitational lens focuses its light before fading back to normal as the planet moves on. The duration and shape of this brightening tell astronomers the mass of the object causing it. It's an incredibly rare and fleeting alignment, requiring continuous monitoring of millions of stars to catch these brief, telltale flickers in the darkness. The implications of these discoveries are truly profound. Early statistical analyses from microlensing surveys suggest a staggering abundance. There could be billions, even hundreds of billions, of these rogue planets wandering the Milky Way galaxy alone. This would mean there are far more planets than stars, and that the predominant planetary environment in the universe is not a warm world orbiting a sun, but a frozen, dark exile drifting in the interstellar deep. This forces us to radically rethink the potential for life. While the surface of such a world would be a frozen wasteland, could life persist deep underground, warmed by radioactive decay or geothermal heat from a molten core, in subsurface oceans similar to those we suspect exist on moons like Europa or Enceladus? A rogue planet with a thick hydrogen atmosphere could even trap enough heat to maintain liquid water on its surface for a time, a temporary oasis in the perpetual night. The idea that the most common abodes for life in the universe might be these lonely, sunless nomads is a concept that completely upends our astrobiological expectations. This vast population of hidden worlds, constantly moving through the spaces between the stars, makes our Orion Arm feel simultaneously more crowded and more lonely. It is crowded with these unseen travelers, a silent flux of frozen worlds passing through our neighborhood all the time. Yet it underscores the profound loneliness of each one, forever separated from the light and heat that could have nurtured complexity. They are the true ghosts of our galactic backyard, the dark, silent majority whose existence reminds us that the cosmos is filled with worlds beyond our wildest imaginings, most of which we may never truly see. And as our solar system journeys through the grand structures of the Orion Arm, it also navigates a much more immediate and intimate cosmic environment, a specific pocket of space known as the local interstellar cloud. This isn't a cloud in the earthly sense of water vapor. It's a region of slightly denser interstellar medium, a tenuous haze of gas and dust that our sun and its planets are currently drifting through. Think of it not as a vast ocean, but as a gentle, localized mist that we've entered and will one day leave behind. This cloud, often abbreviated as the LIC, is our present-day interstellar address, a delicate bubble within the larger emptiness of the local bubble that we call home for this brief cosmic moment. The composition of this cloud is a wispy mixture of elements, incredibly thin by any earthly standard but noticeably denser than the surrounding void. For every thimbleful of this space, you'd find only about 0.3 atoms, a near-perfect vacuum that still manages to be about 10 times denser than the gas inside the rest of our local bubble. Most of it is hydrogen and helium, the primordial building blocks of the universe, but it also contains trace amounts of other elements, microscopic dust grains, and even complex molecules that have been forged in the hearts of long-dead stars and scattered across the galaxy by supernova explosions. We are, in a very literal sense, breathing in an atmosphere that is partly stardust, a diluted cosmic soup that our entire solar system is immersed within. This gentle cloud doesn't have hard, defined edges like a soap bubble. Its boundaries are soft and gradational, merging gradually with the surrounding interstellar space. Our solar system likely entered this particular cloud within the last 100,000 years, a mere blink in geological time, and we are expected to remain within its embrace for another 10 to 20,000 years before moving on into a different region of space, perhaps one with a slightly different density or composition. Our movement through it is a passive journey. The cloud itself is also in motion, and the two of us are passing through each other in a slow, graceful astronomical dance. But this delicate interstellar environment does not reach us here on Earth. We are protected by a magnificent shield generated by our own sun, the heliosphere. This is a vast, teardrop-shaped bubble carved out by the solar wind, a constant supersonic stream of charged particles, protons and electrons, that blows outward from the sun in all directions. This wind pushes against the incoming particles and magnetic fields of the local interstellar cloud, holding it at bay and creating a protective barrier that encapsulates every planet, asteroid and comet orbiting our star. The boundary where the pressure of the solar wind finally balances against the pressure of the interstellar medium is called the heliopause. It's the final frontier of the sun's influence, the very edge of our solar system. The interaction at this boundary is a constant dynamic struggle. As the solar system plows through the local interstellar cloud, the heliosphere is shaped by the flow, compressed on the side facing our direction of travel and stretched out into a long comet-like tail on the opposite side. The Voyager 1 and 2 spacecraft, humanity's most distant ambassadors, have given us our first direct measurements from this mysterious region. They confirmed that the heliopause is not a smooth, hard shell but a complex, porous zone where the solar wind and interstellar medium mix and interact. Here, the solar wind suddenly slows down from millions of miles per hour to a mere cosmic breeze, and the magnetic field of the galaxy begins to dominate. Without this incredible buffer, the interior of our solar system would be far more exposed to galactic cosmic rays, high-energy particles from distant supernova that could potentially affect our atmosphere and climate. The local interstellar cloud is the gentle current we currently sail upon, but the heliosphere is the sturdy hull of our ship, keeping the vast, open ocean of the galaxy from rushing in. This gentle interstellar breeze we currently sail through is a reminder that our cosmic environment is always changing, and while the local cloud poses no direct threat, the history of our spiral arm is written with far more violent events, cataclysms that have, in the deep past, reached across the light years to touch our world. The same stellar nurseries that create brilliant new stars also breed the agents of their own destruction, massive stars destined to die in supernova explosions. These aren't just distant spectacles. When they occur too close to our solar system, they can become a genuine existential threat, and the Orion Arm has both a history of such events and potential candidates for future ones. We know this because Earth's own geological record holds the evidence. Scattered across the ocean floor in a thin, global layer are unusual concentrations of an isotope called Iron-60. This form of iron is radioactive with a half-life of only 2.6 million years. The fact that any of it remains on Earth today is a smoking gun. It could not have formed here. Our planet's natural processes cannot create it. This isotope is exclusively forged in the heart of a massive star moments before it goes supernova and is then blasted into space by the explosion. The presence of these iron-60 layers, dated to around 2.6 and 8 million years ago, tells us unequivocally that one or more supernova occurred close enough to our solar system to literally rain this radioactive dust down onto our planet. The timing of these events is particularly intriguing to scientists, as they loosely coincide with periods of significant climate shift and marine extinction on Earth, suggesting a possible link between cosmic violence and biological upheaval. But how close is too close for a supernova? Astronomers estimate the kill zone for such an event to be roughly 50 light years. Within this distance, the effects would be catastrophic. The initial flash of ultraviolet and X-ray radiation would rapidly strip away Earth's protective ozone layer, leaving the planet's surface exposed to the sun's harsh ultraviolet radiation. This would be followed by a prolonged bombardment of cosmic rays, high-energy atomic nuclei accelerated by the supernova's shockwave. This double assault could trigger a cascade of devastating consequences. The collapse of food chains, starting with UV-sensitive phytoplankton in the oceans, widespread mutations in land-based life, and potential global cooling as cosmic rays seed increased cloud cover. It would be a planetary-scale event with lasting ecological damage. This brings our attention to the present day and the most famous stellar candidate in our sky, Betelgeuse. The brilliant red supergiant marking the shoulder of Orion is a ticking time bomb known to be in the final stages of its life. When it finally exhausts its fuel, it will collapse and explode in a Type Roman II supernova, an event that will be spectacularly visible from Earth even in broad daylight. But is it a threat? Fortunately, no. Betelgeuse is located approximately 550 light-years away, well outside the 50 light-year danger zone. Its explosion will be the greatest astronomical show in human history, but it will not harm life on Earth. The neutrinos it releases will pass through our planet harmlessly, and the light show, while stunning, will pose no physical danger. It serves as a perfect example of a safe yet awe-inspiring cosmic event. The real concern lies with other, less famous massive stars that are both destined for supernova and located much closer to us. One such candidate is Ik Pegasi b, a white dwarf star in a binary system located just 150 light-years away. This object is a different kind of threat. It's not a massive star destined for a core collapse supernova like Betelgeuse. Instead, it's a potential Type Ia supernova candidate. If its companion star transfers enough mass onto the dense white dwarf, it could push it over the Chandrasekhar limit, triggering a runaway thermonuclear explosion. This type of supernova is even more luminous and energetic than a core collapse event. While 150 light-years is still 3 times beyond the estimated 50 light-year kill zone, it is close enough to certainly cause significant damage to our ozone layer and environment, a stark reminder that danger can come in different forms. So, what would an early warning system for such an event look like? Astronomers are constantly monitoring massive, unstable stars in our galactic neighborhood. The very first sign of an impending core collapse supernova wouldn't be the light flash, it would be a neutrino burst. In the final moments of a star's life, as its core collapses, it releases an enormous flood of these ghostly particles. Neutrino observatories on Earth, like Super Kamiok and in Japan, would detect this sudden, intense pulse from a nearby star hours before the light from the explosion even reached us. This would provide a crucial, albeit short, heads-up that a catastrophic event was unfolding in our galactic backyard. We would then know to expect the blinding light show and prepare for the potential environmental consequences that would follow in the weeks, years, and decades after. Our journey through the Orion Arm is a voyage through a region of immense beauty and creation, but it is also a passage through a field where ancient giants occasionally fall, and their final moments echo across the light years. But threading through all these grand structures and violent events, from the vast Radcliffe Wave to the explosive death of stars, there is an even more subtle and pervasive force at work, one that is utterly invisible to our eyes yet fundamentally shapes the very fabric of our galactic backyard. This is the magnetic field of the Orion Arm. We often picture space as a true void, an empty stage where gravity alone directs the show. In reality, that space is threaded with an intricate web of magnetic fields, an invisible framework that guides, contains, and influences almost everything that happens within it. These magnetic fields don't originate from giant cosmic bar magnets. They are woven into existence by the movement of charged particles themselves. Within the vast clouds of ionized gas that drift through our spiral arm, free electrons and protons are constantly in motion. This movement generates electrical currents, and where you have electrical currents, you induce magnetic fields. Once established, these fields are then stretched, twisted, and amplified by the turbulent motions of the gas clouds and the rotation of the galaxy itself. It's a self-reinforcing cycle where motion creates magnetism, and that magnetism in turn guides future motion, creating a complex, invisible tapestry of force that permeates the entire interstellar medium. One of the most crucial roles this magnetic framework plays is as a cosmic ray guide. Galactic cosmic rays are not rays of light, but are actually high-energy atomic nuclei, mostly protons accelerated to nearly the speed of light by distant supernova shocks. These particles scream across the galaxy, and if they reached Earth unimpeded, their intense radiation would make life as we know it impossible. Thankfully, the Milky Way's magnetic field, including the local fields in our Orion Arm, acts as a protective maze. As these charged particles travel, they cannot move in straight lines. They are forced to spiral along the invisible magnetic field lines. This drastically lengthens their journey and traps them within the galaxy for millions of years, bouncing back and forth like pinballs. The magnetic field is our first line of defense, a natural shield that bends the paths of these dangerous particles and modulates the dose that eventually reaches our solar system. Beyond offering protection, this magnetic framework is also a master sculptor in the process of star formation. Within a dark molecular cloud, gravity wants to pull everything inward to form a new star. But the cloud also has internal gas pressure and turbulence that resist collapse. Magnetic fields add a third, crucial force to this balance. They provide a form of structural support, like a skeleton within the cloud, exerting pressure that can powerfully oppose gravitational collapse. For a new star to be born, the cloud must somehow shed this magnetic support. This occurs through a poorly understood process called magnetic ambipolar diffusion, where neutral particles slowly drift through the ionized gas that is pinned to the field lines, allowing the core to gradually contract until gravity finally wins. Furthermore, as a core collapses, magnetic fields help channel the infalling material onto the budding star and also carry away angular momentum, allowing the forming star to slow its spin and avoid tearing itself apart. Without these invisible lines of force, the entire delicate process of star birth would be far more chaotic and inefficient. We can even see the subtle influence of magnetism in the alignment of interstellar dust. Those tiny, microscopic grains of silicate and carbon are not spherical. They are thought to be somewhat elongated or rod-like. As they drift through space, the local magnetic field causes them to slowly spin and align themselves, much like tiny compass needles. This widespread alignment has a visible effect. It polarizes starlight. As light from distant stars passes through these clouds, the dust grains preferentially block or scatter light vibrating in one direction, causing the light that emerges to vibrate in a specific orientation. By measuring this polarization from thousands of stars, astronomers can effectively trace the direction of the magnetic field lines across vast distances. painting a picture of the invisible magnetic architecture of our arm. Mapping this framework, however, remains one of the greatest challenges in modern astrophysics. We cannot see the field directly, we can only observe its effects. Sophisticated instruments like the Planck Space Observatory have mapped the polarization of the entire sky, providing a low-resolution overview of the magnetic field threading our galaxy. For more detailed local maps, astronomers combine many different techniques. They study the polarization of starlight, as mentioned. They also use a phenomenon called Zeeman splitting, where a magnetic field slightly alters the signature of certain radio waves emitted by hydrogen or other molecules, allowing scientists to measure the field's strength. Another method involves observing the alignment of elongated dust grains themselves, which tend to orient their long axes perpendicular to the direction of the magnetic field, a pattern visible in infrared telescopes. What emerges from these painstaking observations is a picture of incredible complexity. The magnetic field of the Orion Arm is not a neat, uniform grid. It is a turbulent and chaotic tapestry, with field lines twisted into knots by supernova shocks, stretched into loops by stellar winds, and ordered into coherent patterns on the largest scale. Its strength is also deceptively weak, typically a few microgauss, millions of times weaker than a common fridge magnet. Yet across the light years of empty space, this faint force exerts a profound and undeniable influence, guiding particles, shaping clouds, and quietly overseeing the birth of new stars. It is the silent, invisible conductor of the cosmic orchestra that is our galactic neighborhood, its presence felt in every process from the smallest dust grain to the largest nebula. Now consider for a moment the grandest structures we've explored so far. The Radcliffe Wave, the Good Belt. But what if I told you there are hints of something even larger and more massive hiding within the data, something that shouldn't be there? Astronomers are now piecing together clues that suggest our local Orion Arm might not be a purely native structure. There is a growing, tantalizing body of evidence that we could be hosting a ghost, a previously undetected dwarf galaxy, or a massive stream of stellar debris that is currently passing through or even orbiting within our cosmic neighborhood. The clues for this hidden behemoth don't come from a direct image. They come from the subtle gravitational tugs it exerts on the stars we can see. The European Space Agency's Gaia mission, which is building an unprecedented three-dimensional map of over 1 billion stars in our galaxy, has given us the tools to see these anomalies. By precisely tracking the motions of these stars, astronomers can detect when large groups of them are moving in ways that deviate from the smooth, expected flow of the Milky Way's rotation. It's like watching leaves floating on the surface of a calm river. If you see a whole patch of them suddenly swirling in an unexpected eddy, you know there must be a submerged rock or a strong current below the surface, invisible to the eye but powerful in its effect. These stellar streams and peculiar motions are the cosmic eddies, pointing to the unseen mass of a dark disruptor. One of the most compelling pieces of evidence comes from the analysis of our galaxy's disk itself. Recent studies have shown that the disk of the Milky Way is not perfectly flat. It is warped and it oscillates much like a vinyl record, slightly wobbling as it spins. While some of this can be explained by the gravitational influence of our large satellite galaxies, the Magellanic Clouds, some models suggest their influence isn't quite enough. There appears to be a need for an additional source of gravitational perturbation, a significant mass that is either passing through or orbiting within the galactic disk itself, right in our spiral arm. This could be the signature of a dark matter-rich dwarf galaxy, one so faint and diffuse that its few stars are lost in the glittering backdrop of the Milky Way's own starfield, its presence revealed only by its gravity. The hypothetical object stirring up this trouble wouldn't be like the bright, large Magellanic Cloud. It would likely be an ultra-faint dwarf galaxy or a completely dark matter-dominated subhalo. Many of these galaxies are known to orbit the Milky Way in its outer halo, but the suggestion that one could be much closer, interacting directly with the disk in the Orion Arm, is a revolutionary idea. Such an object might have only a handful of actual stars, or perhaps even none at all, being made almost entirely of dark matter. Its interaction would be a slow, cataclysmic process, a gravitational sideswipe that sends ripples through the stellar population, disrupting orbits and creating those telltale streams of stars that all move together on a shared, doomed trajectory. The implications of such a discovery would be nothing short of profound, revolutionizing our understanding on multiple fronts. First, it would provide a stunning live-action view of galaxy assembly. The prevailing cosmological model, known as lambda cold dark matter, tells us that large galaxies like the Milky Way grew over billions of years by cannibalizing smaller dwarf galaxies. We see the fossilized evidence of this in stellar streams in our outer halo, like the Gaia Sausage Enceladus stream, which is the remnant of a dwarf galaxy consumed long ago. To find one in the process of being absorbed right now within our own galactic backyard would be like catching the Milky Way in the act of eating a meal, a rare and invaluable opportunity to study this fundamental process up close. Secondly, and perhaps more importantly, it would open a direct window into the nature of dark matter itself. If this object is indeed heavily dominated by dark matter, mapping its gravitational influence on our local stars would allow us to weigh it with incredible precision and chart its distribution. Does the dark matter within it clump in a certain way? Is it distributed in a smooth halo, or are there denser substructures? The answers to these questions would provide critical experimental data to test our various dark matter models, potentially ruling out some and giving weight to others. A local dwarf galaxy would effectively be a dark matter laboratory delivered right to our cosmic doorstep. So, the next time you look up at the familiar constellations of Orion and its neighbors, consider this: weaving its way silently through those stars, hidden in plain sight, could be an entire galaxy, a ghostly island of stars and dark matter, a relic from the early universe that is now commingling with our own. Its discovery would not just add a new object to our charts, it would fundamentally change our story. We would have to acknowledge that our galactic backyard is not just a collection of local stars and gas, but a dynamic and layered cosmic habitat, one that is still being shaped by invisible actors from the deep past, whose gentle gravitational touch is only now beginning to reveal their secrets. And within this dynamic dance of dark matter and galactic structures, our solar system has recently had front row seats to one of the most profound visitors from the depths of the Orion Arm, an event that shattered our perception of the cosmos as a place of isolated island star systems. In 2017, astronomers in Hawaii made a discovery that would ignite both scientific and public imagination. A strange, fast-moving object hurtling through our solar system that was unmistakably not from here. They named it Oumuamua, a Hawaiian word meaning scout from the distant past. This was not a typical comet or asteroid from our own celestial backyard. Its extreme hyperbolic orbit and incredible speed revealed its true origin. It was an interstellar traveler, the first confirmed visitor from another star system. The initial data painted a picture of a truly bizarre object. It had no visible coma, the fuzzy envelope of gas and dust that typically surrounds a comet, yet it exhibited a small but undeniable non-gravitational acceleration, as if something was gently pushing it along in addition to the sun's gravity. Its light curve, the pattern of how its brightness changed over time, suggested it was tumbling end over end and had an extremely elongated shape, perhaps like a cigar or a flattened pancake. The lack of outgassing and its peculiar acceleration led to a flurry of scientific hypotheses. Could it be a fragment of a Pluto-like world from another system, a chunk of solid hydrogen ice evaporating in the sun's heat, or even, in a more speculative but captivating idea, an artifact of alien technology, a light sail from a distant civilization? While the extraterrestrial technology hypothesis was fascinating, the scientific consensus has since gravitated towards more natural explanations, with one of the most compelling being that Oumuamua was likely a fragment of a planet torn apart by the gravitational tides of its home star, a sort of cosmic shard ejected into the galactic void. Just 2 years later, the cosmos sent us a second, far more familiar-looking visitor, 2I/Borisov. Discovered by amateur astronomer Gennady Borisov, this object was immediately recognizable as a comet. It displayed a clear and dramatic coma and a faint tail, the classic signatures of an icy body being warmed by the sun. Its composition, studied by telescopes around the world, was strikingly similar to comets within our own solar system, yet its trajectory was unequivocally interstellar. Borisov's familiar nature was, in many ways, even more startling than Oumuamua's strangeness. It told us that the basic building blocks of solar systems, the icy planetesimals that form in the cold outer reaches of a star's protoplanetary disk, are not unique to us. The processes that forged our own comets are happening identically around other stars, and sometimes those comets get ejected to wander the galaxy. The arrival of these two visitors forces a dramatic reassessment of how much material might be constantly flowing through the spaces between stars. If we detected two such objects in just 2 years with our relatively limited sky surveys, the implied population of similar objects drifting unseen through the Orion Arm must be staggering. Current estimates suggest there could be thousands of such interstellar interlopers within the orbit of Neptune at any given moment, each one too small and dark for us to easily spot until it gets very close to the Sun. The galaxy, it seems, is not a collection of isolated systems but a vast, interconnected network, with a constant, silent traffic of ancient rocks and ice balls weaving between the stars. This raises a profound and thrilling possibility: panspermia on a galactic scale. The Orion Arm, with its mix of young star-forming regions and older stellar populations, could be a vast highway for the exchange of prebiotic material. A comet like Borisov, forged in the cold outer disk of a distant star, could be rich in complex organic molecules, the same kinds of amino acids and nucleobases that are the fundamental building blocks of life. If such a comet were to be captured by a young star system and collide with a suitable planet, it could literally seed that world with the raw ingredients for biology. The impact wouldn't deliver living organisms, but it could deliver the starter kit, potentially tipping the scales on a previously barren world toward the emergence of life. Our own solar system may have been the beneficiary of such a delivery in its early history, and we, in turn, may have launched billions of our own rocky fragments into the Orion Arm through ancient asteroid impacts, potentially carrying terrestrial microbes on an incredible journey to other stars. This constant exchange of material means the Orion Arm is far more than just our home. It is a single, connected biogeochemical environment. The boundaries between star systems are porous, and the story of life on Earth may not be an isolated chapter but part of a much larger galactic narrative. The discovery of Oumuamua and Borisov didn't just add 2 new objects to our catalogues. It opened a window onto a hidden flux of material that has been flowing around us all along, a silent river of cosmic rubble that may have been carrying the potential for life across the light years for billions of years. But all of this cosmic activity, the birth of stars, the abundance of planets, the exchange of organic material, leads us to one of the most profound and haunting questions in all of science. If the Orion Arm is so rich with potential, teeming with hundreds of billions of stars and likely even more planets, then where is everybody? This is the essence of the Fermi paradox, applied not to some distant galaxy, but to our own galactic backyard. Named after physicist Enrico Fermi, who famously posed the question, "Where is everybody?" during a casual conversation in the 1950s, the paradox highlights the staggering contradiction between the high probability of extraterrestrial intelligence and the complete lack of any observable evidence for it. Given the sheer age and size of our galaxy, it seems statistically almost impossible that we are alone. The Orion Arm alone has been around for billions of years, plenty of time for countless civilizations to have arisen, developed technology far beyond our own, and spread across our spiral arm. Their energy signatures, their constructions, their probes, something should be visible. And yet, when we train our telescopes on the cosmos, we are met with nothing but a seemingly endless and silent wilderness. This great silence is one of the most compelling mysteries in our exploration of the local cosmos. One of the most sobering explanations for this silence is the concept of the Great Filter. This theory suggests that there is some kind of barrier, a nearly insurmountable challenge that prevents life from progressing to the stage of becoming a visible, spacefaring civilization. This filter could lie in our past. Perhaps the step from non-living chemistry to the first self-replicating life is astronomically rare. Maybe the leap from simple single-celled organisms to complex multicellular animals is the true bottleneck. If this is the case, then we on Earth are a breathtakingly rare fluke, and the silence is simply the sound of an empty galaxy. The more frightening possibility is that the Great Filter lies in our future. This suggests that the development of advanced technology invariably leads to a civilization's destruction. Whether through nuclear war, uncontrollable artificial intelligence, nanotechnology gone awry, or some other existential catastrophe we haven't even conceived of, every civilization that reaches our level of technological maturity inevitably destroys itself before it can colonize other stars. If this is true, then our own continued existence hangs in the balance, and the silence is a grave warning from the universe. Other theories propose that the problem isn't extinction but transformation. A civilization millions of years more advanced than ours might have moved beyond the need for physical exploration as we understand it. Their goals and their very state of being could be utterly incomprehensible to us. Perhaps they have uploaded their consciousness into a vast virtual reality, living in a perfected digital existence that requires no interaction with the barren physical universe. Or maybe they have become post-biological, existing as forms of energy or information that are completely undetectable to our primitive senses. In this view, the galaxy could be buzzing with activity, but it is happening in a dimension or on a level that we are utterly blind to. They aren't hiding from us, we simply lack the capacity to perceive them, like ants at a picnic unaware of the conversations happening above them. Then there is the zoo hypothesis or the planetarium hypothesis. This idea suggests that Earth is being intentionally isolated, placed under a form of cosmic quarantine or preservation. More advanced civilizations could have a strict non-interference policy, choosing to observe us from a distance as we develop, much like we observe animals in a national park. They are waiting for us to reach a certain level of maturity or technological sophistication before making contact. Alternatively, what we perceive as the universe might be an elaborate simulation or a facade, a planetarium dome designed to give us the illusion of an empty cosmos until we are deemed ready to see the truth. These theories are untestable with our current knowledge, but they frame the silence not as a sign of emptiness, but of a deliberate and carefully managed observation. Perhaps the simplest answer is also the most likely: the sheer scale of space and time. The Orion Arm is vast beyond human comprehension. Even if there are other civilizations out there, their signals might be incredibly brief. A civilization might broadcast for only a few hundred years before moving to a technology we can't detect, like tight beam neutrino communication. We would have to be listening at exactly the right time, in exactly the right direction, with exactly the right technology to catch that fleeting whisper. It's like trying to have a conversation between two ships passing in the middle of the ocean using only flashlights. The chances of them being pointed at each other at the exact right moment are infinitesimally small. Our own radio broadcasts have only been leaking into space for about a century, creating a tiny bubble of noise that has so far barely reached a few hundred of the nearest stars. In the grand timeline of the Arm, our own technological signature is little more than a single, brief blink in the deep cosmic night. Ultimately, the silence of the Orion Arm is a mirror. It forces us to confront our own assumptions about what life is, what intelligence means, and what the future of technology looks like. Our search is constrained by our own human experience. We look for things we can recognize, like radio waves or Dyson spheres. A civilization that has mastered physics in ways we can't yet imagine might use forms of communication and energy that are completely invisible to us. The answer to the Fermi paradox might be that everyone is out there, talking and building and living in ways so alien that we are, for now, functionally deaf and blind to their existence. The great silence, then, is not an answer but a challenge to keep looking, to keep questioning, and to keep developing new ways of listening to the whispers of our galactic neighborhood. So if the Orion Arm is teeming with potential, and the silence might simply be a matter of scale or perception, how do we actually go about listening? The search has moved far beyond just waiting for a deliberate message. Today, astronomers are actively hunting for any trace of technology, any sign that we are not the only builders in this cosmic neighborhood. This is the search for technosignatures, the detectable evidence of advanced technology, and it's a hunt that focuses not on vague hopes, but on the concrete, physical effects such technology would have on its environment. We're no longer just listening for a hello, we're looking for the shadow of an impossibly large structure, the flash of an interstellar lighthouse, or the unnatural chemical signature of an industrial civilization. The most classic and enduring search is for artificial radio signals. For decades, projects like SETI, the search for extraterrestrial intelligence, have methodically scanned the sky, tuning their massive radio telescopes to the water hole, a quiet band of frequencies between the emission lines of hydrogen and hydroxyl that seems a natural, universal channel for communication. The logic is sound. Radio waves travel efficiently through space and can carry vast amounts of information, but the approach has evolved. We're no longer just listening for a powerful, omnidirectional, we are here beacon, which would require an immense amount of energy. The new frontier is in looking for more plausible, efficient signals. This could be a narrowly focused laser pulse used for interstellar communication, a kind of cosmic Morse code that would appear as a very sharp, transient burst of light in our telescopes. Or it could be the faint, leaking radiation from a civilization's own internal communications, the equivalent of our television and radar broadcasts, which have been leaking into space for the last century, creating a faint bubble of noise around Earth. Catching that kind of leakage from another world, however, would require technology far more sensitive than anything we currently possess, as their signal would be incredibly weak by the time it crossed the light years to reach us. Perhaps a more promising approach is to look not for deliberate signals, but for the colossal, unintended byproducts of an energy-hungry civilization. This is where the concept of megastructures comes in. The most famous is the Dyson sphere, a hypothetical concept proposed by physicist Freeman Dyson. The idea is that a sufficiently advanced civilization would eventually harness the entire energy output of its host star. They might not build a solid shell, that's a common science fiction trope, but rather a vast swarm of orbiting energy-collecting satellites that encircles the star. This swarm would capture the star's light and re-radiate the waste heat as infrared radiation. To our telescopes, such a star would look utterly bizarre. It would appear dim in visible light, but would glow unusually brightly in the infrared part of the spectrum. Astronomers have actually gone looking for this exact signature, sifting through data from infrared space telescopes like WISE. They've found a handful of strange stars, like the now famous Tabby star, which showed bizarre and unpredictable dips in its brightness, while natural explanations like swarms of dust or comets are far more likely. These anomalies show us the power of this method. we can search for aliens not by what they're saying, but by what they're building. The search is expanding to include other types of technosignatures that are equally mind-bending. We could look for the chemical signs of industrial pollution in the atmosphere of an exoplanet. Powerful telescopes like the James Webb are already capable of analyzing the atmospheric composition of distant worlds. If we were to find a planet with a balanced, Earth-like atmosphere of oxygen and methane, that would be a potential biosignature, a sign of simple life. But if we found an atmosphere filled with chlorofluorocarbons or other artificial molecules that don't occur in nature, that would be a technosignature, a sign of an industrial civilization actively altering its world. Another idea is to look for the glint of sunlight reflecting off vast orbital habitats or solar panels on a planet's surface, a specific type of reflectivity that would stand out against natural terrain. We could even look for evidence of interstellar spacecraft, perhaps by detecting the waste heat from their propulsion systems or the brief occultation of a star as a large object passes in front of it. What makes this search so compelling right now is that it's no longer purely theoretical. Projects are actively underway, often leveraging vast amounts of data from telescopes designed for other purposes. The Breakthrough Listen initiative is the most comprehensive SETI search ever undertaken, using thousands of hours on premier radio telescopes like the Green Bank Telescope and the Parkes Observatory to scan the 1 million closest stars, the center of our galaxy, and the entire galactic plane. They're not just looking for radio waves, they're also searching for optical laser transmissions. Meanwhile, astronomers analyzing data from the Kepler and Test Planet hunting missions are on the lookout for any anomalous light curves that could indicate the presence of megastructures. The Vera C. Rubin Observatory, when it comes online, will scan the entire visible sky every few nights, providing an unprecedented opportunity to detect transient technosignatures, brief flashes of light, or unusual dimming events that could signify activity. The Orion Arm, our own galactic backyard, is the prime hunting ground. It contains the closest and brightest stars, making them the easiest to study in fine detail. We can analyze the atmospheres of planets orbiting stars like Proxima Centauri or TRAPPIST-1 with far greater precision than we can for distant stars in another spiral arm. Every strange star within a few hundred light-years becomes a candidate, a puzzle to be solved. Is that odd infrared glow just a surrounding debris disk, or is it something more? Is that unusual dimming pattern caused by a cloud of comets or by a fleet of construction satellites? Each natural explanation we rule out brings us one small step closer to a revelation that would fundamentally reshape our understanding of the universe and our place within it. The hunt for technosignatures is the ultimate detective story, a process of elimination played out on a galactic scale, where the prize is the knowledge that we are not the only ones who have looked up at the stars and dreamed of building something greater. Yet for all we're learning from these interstellar vagabonds, the most transformative revelations about our galactic backyard are poised to come not from passive observation, but from a new generation of telescopes and space missions specifically designed to pull back the curtain on the Orion Arm's deepest secrets. We are standing on the brink of a new golden age of exploration, one focused not on distant galaxies, but on our own celestial neighborhood, and the tools we're building promise to rewrite our cosmic address in ways we can barely imagine. Leading this charge is the James Webb Space Telescope, an instrument that is fundamentally an infrared time machine. While Hubble gave us breathtaking visible light images, Webb's infrared eyes are perfectly designed to pierce the veils of dust that have long hidden the Orion Arm's most active stellar nurseries. Imagine pointing this colossal observatory at the heart of the Orion Nebula. Rather than seeing the glowing gas, Webb can peer directly into the dense, dark cocoons of gas where suns and planets are currently taking shape. It will analyze the chemical composition of these protoplanetary disks in incredible detail, identifying the specific organic molecules, the sugars, alcohols, and complex hydrocarbons that are being incorporated into infant worlds. We won't just know that planets form there, we'll know the precise primordial ingredients they're made from, bringing us closer than ever to understanding the raw materials for life itself. Beyond star formation, Webb is also exquisitely tuned to study the atmospheres of exoplanets orbiting nearby stars within our arm. By watching as a planet transits in front of its host star, Webb can dissect the starlight filtering through that world's atmosphere, searching for the chemical fingerprints of water vapor, methane, carbon dioxide, and even potential biosignatures like an imbalance of oxygen and methane that could hint at biological processes. On the ground, the Vera C. Rubin Observatory is set to conduct a revolution of a different kind. This facility won't study one object at a time. It will conduct a relentless 10-year movie of the entire southern sky, night after night. Its enormous 3.2 gigapixel camera will capture the faintest objects ever seen, detecting changes and movements that previous surveys would have missed. For the Orion Arm, this means a complete census of its dimmest residents. Rubin is expected to discover thousands of new brown dwarfs, finally revealing the true population of these failed stars that drift dark and cold between the brighter suns. It will map the proper motions of millions of stars with unprecedented precision, allowing us to trace their paths backward in time and unravel the violent history of the Good Belt and the Radcliffe Wave. Most excitingly, its continuous monitoring makes it the perfect instrument for detecting transient events, the sudden, brief flashes that signify cosmic activity. This could include everything from the predicted neutrino burst of a nearby supernova hours before its light reaches us, to the subtle, recurring dimming of a star that might be caused by an orbiting megastructure. Rubin won't just take a picture of our backyard, it will give it a continuous, beating pulse, but the exploration won't stop there. The European Space Agency's Gaia mission is already meticulously charting the position, distance, and movement of over 1 billion stars, and its ongoing data releases are continually refining our three-dimensional map of the Orion Arm. This data is what allowed us to discover the Radcliffe Wave in the first place, and future releases will undoubtedly reveal other vast, unseen structures woven through our local space. Meanwhile, NASA's upcoming Nancy Grace Roman Space Telescope will combine a field of view 100 times larger than Hubble's with the same crisp resolution. This powerful combination will allow it to conduct wide-field surveys in infrared light, performing a galaxy-wide census of exoplanets using microlensing. Roman could be the machine that finally confirms the existence of a large population of rogue planets, those elusive, starless worlds, by detecting the subtle gravitational lensing effects they create as they drift through the arm. The potential discoveries on the horizon are enough to stagger the mind. Within the next decade, we could have our first confirmed detection of a potential biosignature in the atmosphere of a temperate, Earth-sized world orbiting a star like Proxima Centauri, right in our immediate neighborhood. We might finally find Planet 9, or at last understand the true nature of the gravitational anomalies in our outer solar system, revealing whether it's a captured rogue world or something else entirely. The detailed mapping of dark matter's distribution within our arm could come into sharp focus, telling us definitively whether it's smooth or clumpy, and finally pointing physicists toward its true nature. We might even witness, with hours of warning from neutrino detectors, the eruption of a supernova within a few hundred light-years, giving us a front-row seat to the death of a star and a chance to study its immediate impact on the interstellar environment. This isn't just about adding more facts to a catalog, it's about fundamentally changing our relationship with the cosmos. We are moving from simply observing the Orion Arm to truly understanding it as a dynamic, interconnected system. We are learning how the violent deaths of ancient stars carved out the bubble we live in, how the shockwaves from those explosions triggered the birth of new stars, and how those new stars are now building planets seeded with the complex chemistry for life. The next generation of exploration will show us that our history is inextricably linked to the history of our arm, that the very atoms in our bodies were forged in its stars and its chemistry may have been delivered by its comets. The greatest discovery may not be a single object or signal, but a profound new narrative, that the Orion Arm is not just a place we live, but a place we belong, an active participant in the story of our origins and potentially our future among the stars. This journey through the wonders and enigmas of the Orion Arm ultimately brings us back to ourselves, to a profound realization about our place in this grand cosmic scheme. We are not passive observers looking out at a distant, static universe from a fixed point. We are active participants embedded within a dynamic and evolving celestial environment. Our solar system is a traveler moving through the local interstellar cloud, oscillating through the galactic plane, and sailing past stellar nurseries and the ghosts of ancient supernovae. This positioning grants us a front-row seat to the greatest show in the universe, the endless cycle of stellar life and death, the weaving of magnetic fields, and the silent drift of dark matter, all playing out right in our own galactic backyard. We live inside the very laboratory we are trying to study, a privilege that offers an unparalleled vantage point for discovery. This unique perspective is more than just a lucky accident. It is the very foundation of our understanding of the cosmos. Because we are situated in a relatively quiet suburban limb of the galaxy, far from the blinding radiation and chaotic gravitational tides of the crowded galactic core, we have been able to develop over billions of years. This long-term stability allowed life to arise, evolve, and eventually produce a species capable of looking up and deciphering the secrets of its origins. Our location has provided the clear, stable sightlines necessary to peer into the heart of the Orion Nebula, to witness planet formation, to map the undulating Radcliffe Wave, and to detect the subtle gravitational tugs of unseen objects. The very mysteries we are unraveling are only accessible because we are perfectly placed to observe them. Understanding this intricate environment is far more than an academic exercise to satisfy our curiosity. It is an essential act of navigation, a way of charting the waters we are already sailing. As we contemplate our future as a potential spacefaring civilization, this knowledge becomes our most valuable guide. To venture beyond the protective bubble of our heliosphere and into the galactic mainstream of the Orion Arm, we must understand the conditions we will face. We need to know the density and composition of the interstellar medium, the potential hazards of cosmic radiation and dust grains, and the locations of the safest passageways between the stars. The maps we are creating today of local magnetic fields, stellar streams, and rogue planet populations are the celestial charts for the explorers of tomorrow. This local knowledge also reframes our search for companionship in the cosmos. The Fermi paradox feels uniquely pressing here in our own neighborhood. The sheer abundance of stars, planets, and the building blocks of life within the Orion Arm suggests that if we are not alone, we shouldn't have to look across the vast gulf between galaxies to find company. Yet the great silence persists, forcing us to consider that the answer to whether we are the only intelligent life in this spiral arm might not be found by looking outward, but by looking inward, by understanding the unique and precarious set of circumstances that allowed our own civilization to emerge and survive. Perhaps the filter is behind us, making us a miraculous fluke, or perhaps it still lies ahead, a challenge we have yet to face. Ultimately, exploring the Orion Arm is an act of profound self-discovery. Every brown dwarf found, every stellar stream mapped, and every whiff of a complex organic molecule in a distant nebula teaches us something more about the ingredients and processes that led to our own existence. We are stardust that has coalesced into conscious form, and we are now using that consciousness to trace our lineage back to the very stars and clouds that made us. The Orion Arm is our extended home, a region of space that has nurtured and protected us, and that now presents us with its greatest mysteries as an invitation. To accept that invitation, to continue probing the dark spaces between the stars, listening for whispers, and pushing the boundaries of our knowledge, is to embrace the next great chapter of our human story, one where we step fully into our role as citizens of a vast and astonishing galactic neighborhood. So as we pull back from this grand tour, from the stellar nurseries to the wandering ghosts, a new picture of our galactic home comes into focus. We began with a simple, familiar patch of night sky, but we found a realm humming with activity and brimming with secrets. The Orion Arm is not a static backdrop. It is a dynamic and ever-changing frontier, a place where stars are born in glowing nebulae, where black holes drift silently in the darkness, and where runaway stars tear across the void, leaving magnificent bows of light in their wake. It's a structure built on hidden foundations of dark matter and threaded with invisible magnetic fields that guide the very flow of cosmic evolution. We've discovered that our solar system is not an isolated island, but a traveler navigating vast cosmic structures like the local bubble and the Radcliffe Wave, while interstellar visitors like Oumuamua remind us that the traffic between stars is constant, potentially carrying the very seeds of life itself. This journey transforms the familiar into the extraordinary. The constellation of Orion is no longer just a pattern of stars. It is a window into a colossal factory of creation, with the nebula at its heart actively forging new solar systems. The dark spaces between those pinpoints of light are not empty. They are filled with the possibility of rogue planets, failed stars, and perhaps even the elusive signatures of technologies beyond our own. The great silence of the Fermi paradox is not an answer, but a profound question mark hanging over our spiral arm, challenging us to refine our search and expand our imagination about what life and intelligence could be. Every mystery we've touched upon, from the nature of dark matter to the hunt for Planet 9, underscores a single, powerful truth. Our galactic backyard is a frontier of endless discovery, a testament to the fact that the universe reserves its greatest wonders not for the most distant reaches, but often for the spaces right next door, waiting for a curious eye to uncover them. This leaves us with a renewed sense of place and purpose. We are not just inhabitants of a small planet orbiting an average star. We are conscious participants in a grand cosmic story, living within a dynamic and intricate chapter of the Milky Way's history. The same forces that carved our local bubble and shaped the good belt have influenced the very history of our world, and the same raw materials that coalesce into planets in the Orion Nebula are the stuff from which we are made. To look up at the night sky now is to look into our own extended home, a place filled with both breathtaking beauty and profound mystery. So the next time you find yourself under a clear, dark sky, take a moment. Let your gaze settle on the belt of Orion, and remember that you are looking into the heart of a stellar factory. Remember the hidden worlds that may be drifting unseen, the ancient stellar explosions that forged our environment, and the potential that somewhere out there, another consciousness might be looking back, wondering the very same things. Stay curious, keep wondering, and never stop exploring the incredible secrets hiding in your own galactic